Okay, guys. Yeah, sorry. As you know, I tested positive, so I will be away for 1 week. And so I know you should have finished that part, the accelerate due to gravity last lesson. But I would just try to um, reteach a few ideas because I think this part is quite difficult if you first learn it. Okay, so today's video, I'm going to reteach these parts for like not going to cover everything. So if you've done some work last lesson, so I might just cover one or two examples and that's it. And then I'm going to move on to the next part, which is forces. I will try to finish half of it, and then I'm going to make another video. Okay, the video will be I hope the video will last for 24, 25 or 30 minutes. Okay, so but during the video, you might need to pause the video and do some work by yourself. All right, just tell the teacher you want to have more time to think or to work. Okay, so that's they can pause the video for you. All right, and okay, so it's a acceleration due to gravity, as we know. So the main idea is like we assume under the gravity alone without air resistance, any object will fall to the ground at a constant acceleration of about 9.81 meter per square second, regardless of their masses and shapes. So which is really important. Okay, and of course that's contradicts some of your daily life experience. Of course, if you have tissue spreading out and you and is when you release it at certain heights, it actually it falls to the ground rather slowly than a piece of and then a piece of cake or just a coin. All right, so in daily life, you feel like different objects have different acceleration towards the ground, but that's more because the air resistance. So that's why we assume if air resistance can be neglected, the acceleration will be constant. So it's rather a ideal assumption for the simplicity of our study. Right, and that 9.81 meter per square second is called the acceleration due to gravity g. Okay, so these three pictures here are very important for you to understand. Okay, so trying to try to imagine if you toss a ball upwards and then the ball will somehow reach its highest point and then move down. So in terms of velocity, let's take an upward as positive. So if the ball is moving up, the velocity is positive, and which is decreasing. It's positive but decreasing, right? Okay. And at the highest point, we all know that velocity need to be zero because it's about to turn around. And so at this moment, it's momentarily at rest. We call it momentarily at rest. And then it just after that it's falling downwards. And so in this case, velocity becomes negative, and the v is just sorry, and v is increasing. Okay, so it's negative but become more and more negative. All right, so we see v is changing all the time. V is changing all the time from positive to zero to negative, from decreasing to the increasing in terms of speed. But then how about your acceleration? Acceleration is always downward g. Downward means negative now. So it's negative g. So acceleration is always negative g. no matter what value is v. So the value of a, need to remember this, is independent of v in these cases. All right, a is always negative 9.81 meter per square second, no matter where is the ball in the air. Okay, but v is constantly changing, so that's the major idea you need to remember. Okay, so given that idea, and you can apply the equations. All the equations are applicable. All you need to do, normally you just say, if you take upper positive, then you can say a would be always 9.81. All right, so just remember this. But if you take downward positive, then a, of course, positive 9.81. Okay, then I try to get you to do um, a few examples. Let me check the answers here. Sorry. Oops. Here. Okay, so a dry cells accidentally dropped from the height 100 meter above the ground. So I know the previous answer show you I take downward as positive, but here, and let me try to be consistent with today's video. I will try to take upward as positive. All right. So when we say something dropped from a height, so that means u equals 0, height 100 meter, so that means s equals 100, negative 100 meter. Okay, so, and again, I'm taking upward as positive, so that actually means your a need to be negative 8.81. Right, so which equation can we use to find the time taken? Time taken is t. Okay, so we might just use this formula. Okay, s equal ut plus 1/2 at squared. So s is minus 100 meter, u 0, t is there, h minus 81 t squared. All right, so, and to solve this one, all you need to do is to put all the numbers to the other side. You can get like, okay, all right. That should be negative on both sides, but you are going to cancel out the negative sign, and you will have this. So then you just take square root of the whole thing, and the time just, okay. All right, the next question is speed upon reaching the ground. All right, so you can use, because right now we've got time, but if you use original condition, USA, you can use this formula. So V is what I'm looking for, and A is minus 9.81, and S is minus 100. So just taking square roots of everything here. So just, okay, so if you take square root of this one, you get 49.3 something. Okay, I need to double check with my calculation on the answer, but that answer is quite blurred now. I can't see it properly. Yeah, that's 44.29 meter per second. Okay, so this solution is a bit different from the solution I put onto the OneNote. But okay, you can use this one. In this solution, I take upward as positive, so that's why you can see I put those downward vectors or negative. But if you take downward as positive, you can still get the answer. Okay, the second one, a fish leaps from the water surface and reaches a maximum height of 0.5 meters. What happens here if you have a fish here? Let's say it's a fish, okay, and just somehow jump into air. Okay, I'm not the best drawing, but anyway, you know what I mean. Okay, so you need to find the speed when you just leave the water surface. So that means what you need to find is u. Okay, so that's u. You need to find out. Reach a maximum height of 0.5 meter. Okay, so I would say this is 0.5 meter. And all right, so what else? And that's it. That's all the information you should have. All right, and how can we find? All right, so let's take upward as positive. So that means you have that's s. You have s equals 0.5, and but we need three quantities. What else? Remember, this is maximum height. It's not any other height. It's a maximum height. At a maximum height, the fish need to be momentarily at rest. So remember that when maximum height is mentioned, that means the object is momentarily at rest. So maximum height actually means v must be 0 at that point. So right now you have v equals 0, s equals to 0.5 meter. But again, you need to know a is always 9 minus 9.81 in this case, because we take upward as positive. So which formula can get we the u? Okay, again, we can use this formula. All right, so v is 0 and u is something we don't know, 0.5, 9.81, which is negative. All right, then you will have u squared minus 1 times 9.81. All right, so that means u squared equals 9.1 and u equals 9.81. Take square root. And yeah, so let's say the answer is just this one. Okay, it's a bit off from A because this is for another example. They use different g value in other example. They might use like g equals 10, for example. But it should be answer A. There's no problem, right? And these are the two questions. All right. So and I want to cover today. So make sure you understand the idea. Okay. So let's switch to what should I say? Let's switch to forces. Okay. Um, okay. I need to save it and I set another name. So this is let's say this is a covert version. Sorry. Okay, so for forces, we need to first study a few names. There are four very common forces. All right, the first force we're going to learn is tension. Where can we find the tension? Tension is the force. All right. Okay, sorry. Before the forces, I need to. Sorry, it's my fault. All right. So we need to mention the nature of the force first. And okay, force is something that we all know when we talk about force. You know what it means. Of course, it has some very uh, some other meanings in in movies. For example, in Star Wars, may force be with you. Then that force in physics actually means energy. All right, but forces for us normally means something that we can't see, but we can see their effects. For example, when we say pulling, push, bending, we always mention about there are different ways of applying the force. Okay, so in physics, um, forces can change the state of motion in terms of making a stationary object move, make moving object stop, changing the speed or direction of moving object. Okay, and if you can see, all three things, they involve one thing. Um, they involve acceleration, don't they? Okay, so that means force is related to acceleration, which is a very big idea in Newton's laws. Okay, okay, forces cannot be stored. Okay, so that means force can't be with you, all right, like in Star Wars. Okay, it can't because it cannot be stored. Okay, you either use it or don't use it. Okay, you have to apply the force. When you apply it, you're using it, but you can't store it. Okay, forces must be can only be exerted by an agent. There must be something or someone apply a force on another agent, on another one. Okay, and sometimes force must be applied in direct contact. Okay, like most of the forces we feel, when you feel the forces, normally they are by direct contact. Well, sometimes some forces you can't feel, but um, because they are acting on you through the effect of a field, that means indirect contact. All right, it's like a gravitational field. Okay, so you can't feel the action of gravitational force. All right, and actually there are magnetic field as well acting on some of your electrons, moving electron in your body, but you can't feel it. Why? Because all these forces, they um, most of the time they're acting from a distance. Okay, so normally when forces acting from a distance, um, if you get used to it, you can't feel it until the force is too strong and it force you into certain motion. Okay, then you will feel it. Otherwise, you can't feel it. All right, and the force is a vector quantity, which is important in physics. The unit of force, you all know that must be Newton. Oh, okay, and okay, we use spring balance to measure the forces. Okay, so there are common types of forces. The first one is tension. All right, so where can we find the tension? I just give you a picture so you understand. So if you apply force through a rope or a string, then that would be a tension. All right, all right. So that means tension force exists in falling objects, tall strings, stretch elastic strings, rubber stretch springs, all these things. When you stretch them, that would be tensions. Tensions always exist in pair. They're equal in magnitude but opposite in directions. Okay, in taut or stretch strings, tension points along the length of the string, pulling the objects. Okay, sorry, along the string, along the length of string, pulling the objects at its ends together. For example, okay, so when a man is pulling a load, all right, so you see there would be two tensions, okay, a pair of tensions on the same string, but these two tensions apply on different objects. Like what I've said, each force must have one agent to apply it and the other agent to experience. Okay, for example, this tension is on which one? So this tension is applied by the man and experienced by the load. Okay, remember. Okay, right. So even though you see that tension points towards the man, but tension is a pulling force. It's actually is pulling the load for this tension. So that tension is applied by the man, but experienced by the load. And for this tension, it's quite opposite. So this tension is applied by the load and experienced by the man. All right, so, but there will be a lot of words, are they? So normally we would try to simplify these kinds of descriptions. We might just say by the man and on the load. That would be easier. All right. So that would be our format for the following forces. Okay. And when string breaks, of course, tension disappears. So tension must be on the string, and the string must not be broken. And you're always in pair. Also, always they point towards different directions. Okay. Okay. So you need to indicate directional tension, and you just try to think about what these forces are on and which and by which side and on which object. Okay, so I give you 5 minutes to work on it. Okay, so please pause the video for 5 minutes. I'm coming back soon. Okay, after 5 minutes, so what will be the tensions on this string? All right, so you can see that would be, let's say this is A, this is B, and this tension is by which one? By B on A, right? And that one is by A on B, sorry. Okay, and this one, okay, let's have two. Okay, I'm not going to write everyone, so if you really want to know, you can come to ask me when I'm back. Okay, you just draw all the arrows like this. Okay, for this one, need to be careful. So how many pairs of tensions you will see? There are 3 pairs rather than 2, all right? So 1 pair, second, and third. That's it. All right, and okay, let's move on to next force, which is friction. Okay, friction happens in which cases? So normally, so for example, in your experiment, you should know that there should be a friction for the object moving down slope, all right? But if you're a rolling object, that friction can be neglected, all right, or be reduced, all right? But um, let me give you some ideas here. Okay, in physics, when we say there is a when there is a relative motion, so here's the keyword, relative motion, or tendency of relative motion. That means um, not just a relative motion, but sometimes even there isn't a relative motion, but there's a tendency, it tends to be a relative motion, then it might cause friction. All right. Relative motion between two objects means they move with different velocities. Okay. So, and why do we need to learn relative motion? Because friction always opposes the relative motion. Remember this, they opposes not the motion, but the relative motion, which is very important idea. And also friction exists in pairs too. Soon you will find all those forces, they must exist in pairs. All right, so let's just think about the idea of relative motion. Relative motion, whether there is a relative motion between the two contacting objects or surfaces. Okay, so we just focus on the two surfaces, like for this one, the ground and also the objects. Okay, so the surface is around here. So is there any friction? Okay, so we can see, so is there any relative motion? We talk about friction later. So the object is moving at 2 meters per second and the floor or the ground remains at rest. So uh, that means there is relative motion, right? Okay, so at the same time, if the object is not moving but the floor is moving, and in that case, there is also relative motion because it doesn't matter which moves. It matters when they move relative to each other. Okay, so if the object is moving at 1 meter per second, the floor 2 meters per second. So relatively speaking, the floor is a bit faster. So that means there is relative motion. How about 1 meter per second? Object 1 meter per second, um, floor. Okay, right? And no. Okay, right. Okay, a little bit a little a small activity here. Can you demonstrate um, relative motions with your two hands? Okay, I can't, of course, I can't see you doing that. So you just try to demonstrate or convince yourself and your classmate that you are doing something right. Okay, so I will give you 5 minutes. Please pause the video. Try to think about relative motion on 5 minutes during that 5 minutes. All right. Okay, I hope you get that. Okay, so it's rather easy to demonstrate you have relative motion with two hands. That means one, for example, if your if you put your two hands together, um, facing each other, your two hands, but your left hand is moving a bit faster than right hand, then that would be relative motion. But if your two hands moving together at the same speed, in the same direction, then there's no relative motion. That's it. Okay. And okay. So let's try to indicate the direction of friction, if any, on the object. Okay, so let's go back to see this important um, statement. Friction always opposes the relative motion. So friction always try to stop the relative motion. That's what I'm going to say. So if there is a direction of motion on for the object towards the right hand side, where would be the friction acting on the object? So you only need to draw the friction on the object. All right, so the friction on the object will actually be on the object, but the object is moving to the right. Okay, so friction must be to the left. Okay, the next one is a bit like the situation in your experiments. So the object is sliding down the incline. All right, so where should be the friction? Friction must oppose that motion down the slope. So friction should be here, should be in that direction, right? Okay, you see the word rough. What does it mean? It means the incline, the surface is rough. That means there will be friction. So the opposite is if they say smooth surface, that means frictionless. Okay, so if that's smooth surface, then you don't need to consider friction. Okay, even though they have relative motion. Okay, walking. So we can see. So let's draw it. So like here. So when you're walking like that, you say your body is moving forward, right? So you might think, okay, my body is moving forward, so your body is in relative motion with the floor. So you might think the friction should be in the opposite direction to your motion. So is the friction should be in that way? But that actually was wrong. Why? Because remember that friction is to oppose the relative motion between two contacting surfaces. So that you must take consideration of the surfaces which are in contact. So your body is not in contact with the ground. We're not snakes, right? So your body is not on the ground, but your feet are. So let's consider this. If when you are moving forward, actually what happened to your foot is your foot tends to slip backward. Okay, so for friction, you will try to oppose your foot slipping from slipping backward. So the friction will be forward. So in that case, if I draw the diagram here, hmm, what do you think? Actually, that's correct one. Even though you might feel a bit weird because friction and V they are in the same direction, but that's correct. Why? So because from friction's perspective, it doesn't matter where what's the movement of your body, what's the direction of motion of your body. It does matter what's the relative motion between the foot and the ground. And when we are walking, your foot's always moving backward. Yeah. So that's why the friction is always forward. So in that case, wait, see there are three cases. So in the first two cases, you can say the friction actually opposing the whole motion of the object. But in the last case, the friction only opposes the motion of your foot, but actually is helping the motion of the whole body. Okay, so that's very important idea because friction can help the whole body moving forward. Okay, right? So that's very important idea. So friction can resist the motion like the first two examples, but it can help as well. especially in walking. Okay, let's try to think about this question. Okay, a horse pulls a block along a rough horizontal road and moves with uniform velocity, which following correctly describe the direction of friction from the ground acting on the horses. Okay, friction from the ground acting on the horses and block. Okay, just give you some time to think about the idea. Okay, so you might spend 2 minutes to discuss that among yourselves, and you need to convince others to follow your idea. Okay, good. Okay, so let's assume 2 minutes up. So what's your answer? So for me, okay, obviously for both block and horse, both are moving forward in terms of their V. But then when I'm considering where the friction will happen, I consider the contacting surfaces. Okay, for the friction acting on the block, obviously is sliding on the surface. So the relative motion for that contacting surface is forward, right? So that means the friction must be backward. Okay, but how about for the horses? You know, when horses are running and is feet just like human beings. I don't know if there's any animal they can walk like them. The feet are moving forward and the animals also um, moving forward. I can't see, but it's physics. In physics, it's impossible to happen, right? So let's assume that the horse is just as normal as human beings. So that means the friction should be forward because we assume his feet is going to move backward, right? So the friction is helping the horse to move forward, but it's resisting the block from moving forward. Okay, so the answer is D. All right. All right. So in conclusion, we understand. Um, okay, if friction depends on maximum value, so because there's involved another force called normal force, and we haven't talked about this. Um, so, but anyway, friction depends on the roughness and depends on how tight the two surfaces are, which is quite um, which is um, in line with our intuitive ideas. So and in conclusion, friction can help, and friction sometimes it doesn't help. When you are walking, moving on a road, because you got wheels rolling backwards, and writing, you need friction to help you to write words in certain pattern because you need to turn around, you need to stop sometimes for the pattern, and braking, you need friction to help. But it doesn't help when there's a moving part in machine. It causes all sorts of noise, dragging objects, just like dragging a block like the horse does in the previous example across the floor. All right. So just refer back to our experiment. So when you're using a ball bearing rolling down that incline, you should understand the friction actually it helps rather than resisting the motion. So that's why when you are using the rolling ball bearing, we don't need to consider friction that much. Okay, and okay, so ways of increasing and reducing friction, increase the bumpiness, and that's quite obvious. For example, the groove in tires, reducing, you smoothing out the surface, lubrication, ball bearings, good ideas. separating surface with air. Okay, so certain games, if you play, they have like a disc game. I forgot the name. So like you pay the money, they have certain air from the small hole. So the disc is just a little bit flowing air. So the disc can travel pretty fast. All right. Anyway, yeah, that's it. Okay, so I can. I think that will be it. Okay, so next lesson I will try to do the remainder of this handout. All right. Okay, and you can always go to OneNote if you want to see more of it. Okay, so thanks for watching the video, and thanks for the teacher, whoever it is, helping to broadcast the video and also post the video. Thank you. Really appreciate it. Thanks. See you next time.